Howdy, howdy, howdy. So let's talk about MyAP quiz and Newton's second law. A lot of the stuff, Newton's second law, you know that if an object is balanced, it is not going to accelerate. And if it's unbalanced, it is going to accelerate. All right. So a lot of the stuff on that is just talking about objects that have an unbalanced force, have a force that's greater in one direction and learning how to deal with the forces that are unbalanced. But a couple of things we haven't really talked about. An interesting thing is if you take a hammer and if you throw it in the air, right? It doesn't rotate around the center of the hammer. It actually rotates around the center of mass of the hammer. And so it will rotate right around this spot. So this handle will swing in this wide range, and the head will swing in this small circle. It won't swing like this. So the truth of the matter is, when you have any two masses, um, like for instance, if you have a small satellite, it says, "Does the moon revolve around the Earth?" And then it says, "Does a small satellite revolve around the Earth?" And so, if you have a very small satellite, something super light, and it's maybe this far away, but it's super light. The Earth is 6 times 10 to the 24th kilograms. So the Earth is massive, and a satellite is like maybe I don't know 1,000 kilograms. I don't know what it is. Maybe 100 kilograms, depending on the satellite. And so it makes zero difference. The center of mass, it is going to rotate around the Earth. The center of mass is pretty much the center of the Earth because the Earth is so massive in comparison. However, the moon is actually sufficiently massive that the Earth actually wobbles in its path. And so as the moon goes around, it doesn't actually go around the center of the Earth. It goes around this point right here, which is approximately, I don't know, 4/5 of the way to the to the crust, actually. And so as the moon goes around and the Earth goes around, they kind of, I'm not sure if you can see my hands in this case, they kind of wobble around each other. If you can picture like maybe a double star system, like in Star Wars, they have some binary systems, and the stars are in the center, and the stars are rotating around each other, right? And so, anyways, the objects actually rotate around the center of mass. We'll learn more about center of mass when we get into momentum. But right now, there's a question that talks about center of mass um, on the Newton's second law, and I just wanted you to have a little bit of a introduction to what that's talking about. Okay, there's actually a lot of questions that come up in physics about elevators, and so let's just talk about elevators for a second. And so here you have a picture of a person standing on a scale. And so this person standing on a scale. And then if you look at the force diagram, the scale is the reading on which is Fn. And so the scale is the reading of Fn in this situation because the person's on flat ground and their weight is mg. That's their weight. And so that makes sense. And so the acceleration is non-existent. They are not accelerating up or down. So in a elevator, you could be going at a constant rate or standing still, and at a constant rate, which would be dynamic equilibrium, or standing still, which would be static equilibrium. The elevator reading would be this. Your scale reading would be normal, and the elevator would be pushing up on you at the same amount of force as your weight. And that's actually true whether you're moving or you're not moving. Static electricity equilibrium or dynamic. Let's look at Newton's second law with respect to elevators, though. With Newton's second law, if you were to accelerate up, how do you do that? Well, you actually have to push harder than gravity. And so if you push harder than gravity, the normal force goes up, and for a second, when you go upward in the elevator, you actually feel heavier. You'll feel, oh, I feel a little bit like, oh, it's pushing down on me. And so you'll feel heavier because your acceleration is up. Now, this makes sense. Your forces are unbalanced in the upward direction, and so you are accelerating upward. Okay? And then the last situation, of course, if you're accelerating downward, and so when you get to the top, what will happen is um, perhaps it won't have any upward force. Like literally, that would be like a really quick stop. Well, let's say it has a little bit of an upward force, so your normal force is still there, right? So you'll feel lighter than you normally would. So you're feeling lighter. Now you got to remember that you can also throw in direction. So your body will react or feel differently depending on which direction you're going as well. And so that would be, there's a question of which direction is your velocity. Are you starting from rest? Are you starting from motion? Yeah, you got to consider those things. But when we're talking about force diagrams, who cares, right? Because this is just showing that the net force is up, and so your acceleration has to be up. I don't care about the velocity. I could change the velocity. The velocity could be up, and you'd be going faster. But if the velocity was down, you'd be slowing down. In that case, in this case, if the velocity was up, you'd be slowing down. But if the velocity was down, you'd be speeding up. So that's inconsequential, really. What's consequential is Newton's second law, which is saying that the forces are unbalanced in the downward direction, so your acceleration is down, and the forces are unbalanced in the upward direction, so your forces are up. In this one, the scale would read heavier because, once again, the scale is read by the normal force. In this one, the scale would read lighter. And so, I don't know. Hopefully that helps you answer those questions with respect to Newton's second law on that quiz. Remember to ask me questions in class or on email if you have questions about these quizzes. Okay, have at it. Have a good time. Have fun.